So in our last video, we looked at the primality test, the square root primality test, which told us how far we really need to check for prime divisors. And we did more with prime power factorizations. Now we want to move on to special types of primes and some open problems. And we'll even go further and looking at greatest common divisors. So to begin with, we want to define what a Mersenne prime is. So a Mersenne prime is a very special kind of prime. So people have been investigating primes now for several hundred years, trying to look at their structure for several hundred years. They have been saying, okay, we have these prime numbers and they continue on forever. We know they go on forever. But how do we find a next prime? How do we find a next prime? So that's a big topic in number theory, is finding the next prime number. So back in the sort of late medieval, early kind of Renaissance period, there was a mathematician. He was actually a monk. He was a monk from France. His name was Mersenne. His name was Mersenne. He was investigating primes and their structure. And he noticed that when he had the formula 2 to the n minus 1, he got a lot of primes. So any prime that is of the form 2 to the n minus 1, where n is a positive integer, is called a Mersenne prime. Let's look at some of these primes. So let's just do some examples here. Examples of Mersenne primes. So if I had 2 to the 1 minus 1, that would just give me 1. That's not a Mersenne prime. Because it's not even prime, right? 1's not even a prime number, not a Mersenne prime. What if I had 2 to the 2 minus 1? That'd be 4 minus 1. That'd be 3. That is a prime. So this is a Mersenne prime, if I can spell Mersenne. What if I did 2 to the 3 minus 1? That would be, what, 8 minus 1, 7. That's prime, so it's a Mersenne prime. What if I did 2 to the 4 minus 1? Well, that'd be 16 minus 1, that's 15. That's not even prime, so not a Mersenne prime. What about 2 to the 5 minus 1? Well, that would be 32 minus 1. That would be 31. That's a prime, so it's a Mersenne prime. And let's say I did 2 to the 6 minus 1. So that's 64 minus 1 is 63, sorry. 63. 64 minus 1 is 63, so that's not even a prime, so it's not a Mersenne prime. Add 2 to the 7 minus 1. That would be, let's see, 128 minus 1. 128 minus 1, that's 127. 127, that is actually a prime, yeah, so this is a Mersenne prime. 127 is prime. How could you check if 127 is prime? Well, you could take the square root of 127, which is 11 point something, do the floor of that, which is 11, and then just check if 2, 3, 5, 7, and 11 are factors of 127. None of them are, so it is a Mersenne prime. And you can keep going, finding more. So 2 to a power minus 1 isn't always a Mersenne prime. Sometimes it is, sometimes it isn't. Here's an important fact. Important fact. If P is of the form 2 to the n minus 1 is a prime, so that means it's a Mersenne prime, then n must also be prime. So for example, notice when we had the primes, the red ones. So we had 3, 7, 31, and 127. These are the Mersenne primes we have so far, right? 3, 7, 31, 127. So that's our P. Notice that when the P, 3, 7, 31, 127 was prime, then the powers, 2, 3, 5, and 7 were also prime. So when the P is prime, then the n must also be prime. But be cautious. Just because the n is prime, that doesn't mean the P will be prime. So just because n is prime does not mean that P equals 2 to the n minus 1 also is prime. Yeah, sometimes you can find instances where the n is prime, the exponent is prime, but the number P itself is not prime. Yeah, so these are called Mersenne primes, and they're an interesting place to look for more prime numbers if you want to find a new prime number that you're not familiar with. And some people look in there, in that direction for new prime numbers. 2 to the n minus 1. Okay, so this is something in number theory that's of interest of number theorists. Here's some other problems that are of interest to number theorists. These are famous open problems. Famous open problems in number theory. An open problem means it's an unsolved problem. It's a problem that's been around a long time, but that hasn't been solved. So probably if you were to solve these problems, you would make, they'd probably give you a prize of money. Who knows how much. So one is called the Goldbach Conjecture. This one's been around since the 1700s. It says this. So we don't know if it's true or false. Every even integer, n, greater than 2, is the sum of two primes. This is something that many mathematicians believe is true. They've gone through and tested it for millions and millions and millions of even integers, even billions possibly. I'm not sure how far they've gone. Probably billions of even integers. They've tested it and shown it's true for those. But they don't know if it's true for all even integers. There may be an even integer way out there that's really big, super big, that they haven't tested yet, that it may not be true for. What this is saying is every even integer, so that would be starting with 4, and then 6, and 8, and 10, you can write it as a sum of two prime numbers. Now, it looks like it's true, so let's start with 4. That can be written as two primes added together, right? 2 plus 2. 6 is the next even integer. You could write that as 3 plus 3, 2 primes. 8, you could write that as 3 plus 5, 2 primes added together. What else? 10, you could write that as 5 plus 5, 2 primes added together. 12, you could write that as what? 5 plus 7. 14, you could write that as 7 plus 7. 16, you could write that as, what could you write that one as? 5 plus 11. and so on. So people have checked the even integers from 4 on up for billions and billions, millions and millions at least. I know millions and millions, maybe billions of even integers. They've shown it's a sum of two primes. But is it true in general? We still don't know. And if you can prove it's true or prove it's false, you would solve a problem that has been open for several hundred years. So also there's something called the twin prime conjecture. Twin prime conjecture. And this just says there are infinitely many twin primes. We don't know if it's true or false. So what is a twin prime? A twin prime is a prime that's just 2 spaces away from another prime. So let's look at some examples here. Let's look at 3 and 5 are twin primes. What else? 5 and 7. What else? 11 and 13. 19. No, not 19. 17 and 19. What else? 29 and 31. Anything else? I think off the top of my head. Can't think of any, but I don't have a long list of primes in front of me, but it turns out people have checked this for many, many primes, millions, if not billions of prime numbers. And all primes don't come in pairs, but there are infinitely many of these pairs of primes that are just a space of 2 apart. That's what it looks like. That's what it looks like. People think. But who knows? Maybe when you get way up there, way up there in the trillions of digits, maybe there aren't any primes that are just a space of, maybe they stop somewhere. So no one's been able to prove whether this is a true statement or a false statement. It looks like it's true. So if you can prove it's true or prove it's false, you can get a lot of money, I bet. Okay. So what we want to move on to now is what is a greatest common divisor? Definition. So we're going to define the greatest common divisor. Suppose A and B are integers, and they're both not 0. So A could be 0, but if A is 0, then B is not 0. B could be 0, but if B is 0, then A is not 0. So they both can't be 0 at the same time. The greatest common divisor of A and B, sometimes also called the greatest common factor of A and B, denoted GCD, A comma B, is the largest integer D such that D is a factor of both A and B. So the greatest common divisor of A and B is the largest integer that is a factor of both A and B. Now, for example, if I wanted to find the greatest common divisor, GCD of 30 and 45, I could look at the factors of 30, which are, what are the factors of 30? 1, 2, 3, 5, 6, 10, 15, and 30. Those are the positive factors. And then I look at the factors of 45. 1, 3, 5, 9, what else? 15, and 45. So first I have to find one that's in common. So it has to be the largest one that's a factor of both of these numbers. So in common, we have 1 in common. We have 3 in common. We have 5 in common. We have 15 in common, and the largest is 15. So the GCD here is 15. So the answer is 15. The GCD, the largest common factor, the greatest common factor, the greatest common divisor is 15. You can do it that way. Now, if you can do a prime power factorization, there's a much more efficient way of doing that. So for example, if A has a prime power factorization of P1 alpha 1, P2 alpha 2, through Pk alpha k, and B has a prime power factorization of P1 alpha 1, P2 alpha, I'm sorry, not alpha, beta. I'm going to use betas for my exponents of my B's factors. So B is going to be P1 beta 1, P2 beta 2, and so on and so forth, P k beta k. With the PI's prime, so each of these PI's are prime with the PI's prime. And the alpha i's and beta i's are going to be greater than or equal to 0. They could be 0. They're going to be integers greater than or equal to 0. Then the GCD of A and B is going to be, you take your first common prime P1 and you look at the minimum of the exponents. Alpha 1, beta 1. And then for P2, you copy down that second common prime and you look at the minimum of the exponents, alpha 2, beta 2. And you continue this procedure. For the last common prime, Pk, you write that down and you look at the minimum of the exponents alpha k and beta k. And that is an efficient way for doing the GCD. But you can only do this when you have a prime power factorization. Now let's see how exactly this works. Exercises. Find the GCD of each pair of integers. So number 1, we have what? 3 to the 5th times 5 squared times 11. That's our A. And for B, we have, let's see, 2 to the 3rd times 3 squared times 5 times 11 to the 4th. So luckily, we already have our A and our B in prime power factorization form. So when we find the GCD here of these numbers, A and B, we're going to take the common primes. So what primes do they have in common? Well, they both have a 3 prime in common. They both have a 5 prime in common. They both have an 11 prime in common. Now it looks like B has a prime with a base of 2. Right? You have 2. 2 to the 3rd. A doesn't have that, but what you could do, you could rewrite A. You could write A so it's actually 2 to the 0 power. Come on, if I can get this to work, it's not working. I could say 2 to the 0 power times, if I get this to work, 3 to the 5th times 5 squared times 11 to the 1 power. So even though A didn't have a 2 prime, I still made it 2 to the 0 power. Okay, So now we can say we have common primes 2, 3, 5, and 11. So when I'm finding the GCD of these two numbers, A and B, I'm going to start with my common prime, 2. And then I'll put the smallest of the two exponents. The smallest of the two exponents, the 0 and the 3 here, is going to be 0. Then I multiply, and I put my next common prime, 3, down. And I look at my powers, 5 and 2. 2 is the smaller one, so I'm going to put the 2 there. Then I go on to 5, the common prime 5. Notice we have a 2 and a power of 1, so I'm going to take the smaller power of 1. And finally, for 11, I'm going to copy that prime down that's in common. I'm looking at my exponents 1 and 4. 1's the smaller one, so I'm going to include a 1. So we have what? 2 to the 0 times 3 squared times 5 times 11. That's basically, let's see, that's going to be what? 9 times 5 times 11. Let's multiply that out. 9 times 5 times 11, 495. Our answer here is 495. That's our GCD of these two numbers. Number 2, we have 2 to the 4th times 3 times 5 squared times 11 times 13 as A. And for B, we have, let's see, 2 squared times 3 to the 4th times 5 times 13. So A has a 2, a 3, a 5, an 11, and a 13. B has a 2, it has a 3, it has a 5, it's missing an 11, and it has a 13. So since it doesn't have an 11, we're going to put 11 to the 0 in there. So I'm going to rewrite this as, if I can get this to right, I'm going to rewrite this as 2 squared times 3 to the 4th times 5 to the 1. And here we go with the 11. We're going to write times 11 to the 0 power. We don't see an 11, so we write 11 to the 0 power, and then times 13 to the 1 power. All right, so now we're ready to find the GCD. I will use, for color, I'll use this kind of orange color. The GCD of A and B equals, so we're going to take our common primes here of 2, and the smallest power is going to be the 2. Then we're going to take our common primes of 3, the yellow ones, and the smallest power here is going to be the 1 power, right? You got 3 to the 1, 3 to the 4. 3 to the 1 is what we're going to take. And for the 5s, I'm going to write down a 5, and the smaller power is going to be the 1 power rather than the 2 power, so 5 to the 1. And for the common 11 here, we created 11 on the B. We're going to take the smaller power of 0, right? 0 is smaller than 1, so 11 to the 0. And then finally 13. They both have a 13. This one's to the 1, this one's to the 1. Well, the smaller power is 1. When they're the same, the smaller power is 1. So what do I got? I got 2 squared is 4 times 3 times 5. 11 to the 0 is just 1 times 13. When I multiply that out, 4 times 3 times 5 times 1 times 13, I believe I get 780. 780. So the GCD of those numbers, A and B, is 780. All right, this last one, number 3, here we go. We have A is 4,410. We have B is 2,058. Well, unfortunately, this one is not factored for us, so we're going to have to do a little factoring. So I'm going to factor, let's see, 4,410. It's divisible by 2. Let's see, 4410 divided by 2 is 2205. That's divisible by 5 for sure. 5 is a prime factor. You get 441. That's divisible by 3. 3 is a prime. Let's see, 441 divided by 3 is 147. That's divisible by 3. 147 divided by 3 is 49. You can break 49 into 7 times 7. So I can write the prime factorization of A as, let's see, 2 to the 1. That's my 2 right there. 3 squared. Right, I have 2 copies of 3. 5 to the 1. And 7 squared. All right, now let's do the B. Let's do the B. 2058. I'm going to have to erase here and do a little factor tree. $2,058. That's divisible by 2. You get 1,029 when you divide that by 2. 1,029 is divisible by 3. Divide that by 3 and you get 343. 343 is divisible by 7. You get 49. 49 breaks up into 7 times 7. So the prime factorization here is going to be, let's see, B is going to be 2 to the 1 times 3 to the 1. No 5s, right? So we're going to write 5 to the 0. And how many 7s? We have 3 7s. 1, 2, 3 times 7 to the 3rd. All right, so when I find the GCD here, what color am I going to use? GCD, I'll do an orange again. GCD of A and B, it's going to involve a 2, right? They both have a 2 in common. The smallest among those is 1. They both have a 1. Then a 3. The smallest power here is 1 times 5 to the 0 power, right? 0 is the smaller power. And then we got times 7. The smaller power is the 2. So let's see, that's 2 times 3 times 1 times 49. And I multiply those together. 6 times 49, basically. Let's see. GCD here is 294. All right, so that is going to be it for this video. And we'll actually continue looking further. In the next video, we'll look at the concept of relatively prime. And we'll look at something called the Euler-Tauschen function. And we'll look at,